All right, so let's begin. Hello everyone, I am Srishi Siddharth. I am a PhD student associated with the Center for System at IIT Bombay. Also the TA for the course, Senior Dynamic. Welcome to 8th week student session. So let's begin with the review of topics. Uh, all right. So in today's session, we are going to talk about stabilizability, detectability. So we have PBH test for both of them. Then we're going to focus on design of state estimators. We are just going to look at how to obtain the observable canonical forms. So just a second. Let's start with the question and then we recall the definitions of the statements of the previous test for stabilizability and detectability. So let's begin. So consider the LTI system. X dot equals minus 2, 3, 0, 4, x. And then we have this B matrix and y equals 0, 1, and 6. We are considering the output as the second string. So we have to talk about stabilizability and detectability for the system. Let's recall. For the PBH test for stabilizability. So the matrices that we talk for controllability and stabilizability are the same. So that's rank of A minus lambda I B. That should be equal to the order of the system. And for stabilizability, we want lambda such that their real parts are greater than 0. So for all lambda complex, and similarly for PPH test for detectability, for that the matrices for detectability and observability are same. So we have rank of A minus lambda I, and C here, that should be equal to N. Again, for all lambda, such that the real parts are greater than equal to 0. For this, we first need to calculate the eigenvalues of A. So let's begin. We need to find the eigenvalues from the characteristic equation. This is minus 2 minus lambda. Then 4 minus lambda. 3, 0. Minus 2 minus lambda. 4 minus lambda equals 0. So we have lambda plus 2 equals 0. And minus lambda equals 0, which implies lambda equals 4. So we just have to consider this positive eigenvalue for the PBHs. So A minus lambda I for lambda equals 4 is, this is going to be used in both the tests. This is minus 2 minus 4. This is 0, 0, 0. Alright. So we have stabilizability. Its rank of, let's form that matrix, minus 6, 3, 0, 0. And then the B vector, that's 1, 0. So this is a whole row of zeros. So you can see that there is only one linearly independent row. Therefore, the rank is 1. Therefore, the system is not stabilizable. Let's talk about detectability. Of A minus 4I, so that's minus 6, 3, 0, 0. And then C, that's simply 0, 1. This is a row of zeros. These two rows are linearly independent. We can just check this pretty quickly. Alpha 1 minus 630 plus alpha 2 0 1 equals 0. We have the first equation which implies alpha 1 equals 0, and the second equation is the two rows are linearly independent, therefore the rank is 2. Therefore the system is detectable. These tests are clear to you. If you have any questions, you can ask me. Otherwise, we'll move on to the next question. Right. If not, let's move on. LDI system. By the following matrices. Matrix A as 0, minus 2, 1, minus 2. C is 0, 1. We have to find the gain matrix K. To place the eigenvalues. at the desired locations. Let's say that the desired eigenvalues are located at, uh, let's say D1 and D2. So second order system, we have two eigenvalues. And if they are complex valued, then D1 and D2 should be complex conjugate pairs. Alright. Now let's also form the desired characteristic equation. That is simply going to be S minus D1, S minus D2 equals 0. This is simply S square minus D2S minus D1S S D1 D2 equals 0. So the sum of eigenvalues and the product of eigenvalues. This is the desired characteristic equation. Alright. Now we have to place eigenvalues of A minus KC. So we have A minus KC. Let's first determine the dimension of the K matrix. So this is 2 by 2. This is a row vector, so 2 by 1. So this should be 1 by 2. Sorry, this is a row vector, so this is this, and then 2 by 1. So K is a column vector. Let's say we have K1 and K2. So A minus KC is going to be 2 minus 2, 1 minus 2, 2, and then we have C. Comes 0, K1, 0, and K2. Alright. Then we can simply subtract these two matrices. We have minus 2 minus K1, 1 minus 2 minus K1. Right. Now we want the desired eigenvalues of this matrix A minus Kc to be the same as this characteristic equation. So let's form the characteristic equation of A minus Kc. Determinant of A minus Kc minus Si equals 0. So this is minus S minus 2 minus K2 minus S, and the off diagonal entries remain the same. This should be 0. Alright, so let's conclude this determinant. S plus K2S plus S square plus 2 plus K. S is K2 plus 2. So we have two characteristic equations. We can compare their coefficients and get the values for K1 and K2. was the sum of eigenvalues. Let me just check again. Yeah. Minus d1 plus d2. Yes, k2 plus 2. So this is simply. And when we have the product of eigenvalues, so we have 2 plus k1 equals d1 d2, which implies that k1 is simply d1 d2 minus 2. So given the two eigenvalues, we can form the gain matrix easily by substituting these values. So the gain matrix K, in this case a column vector, is simply and minus d1 plus d2 plus 2. So this places the eigenvectors of A minus Kc at the desired location. So I hope that this question was clear to you. We can also find a similar uh, formula for the gain matrix for a third order system as well. You can try that out. So we are going to look at a third order system in the next question. If you have any doubts, you can ask me in this question. You can observe that this was very similar to the process for finding the gain matrix such that we can place the eigenvalues of A minus BK at the desired location. So we have simply just did this for the pair AC instead of AB. Alright. Next question. Consider the matrices T 0 0, 5 0 minus 1, 4 minus 1 0. And we have CS 1 minus 1 9. So we have two parts to this question. First one is to verify whether the pair CA is detectable. One is find the gain matrix L such that A plus LC is a Hurwitz matrix. So we can also have another question which asks us to find the gain matrix L such that A plus LC has some desired eigenvalues. But in this part, we just need simply A plus LC to be a Hurwitz matrix. Alright, so the first question is simple. We have to use the PBH test for detectability. So for that, we need the eigenvalues of A. Okay. Alright. So element of A minus lambda I equals 0. We simply have 3 minus lambda minus lambda minus lambda 0 0. So we have a lower triangular matrix that simplifies the calculation of determinant. So we simply have 3 minus lambda times lambda square minus 1 equals 0. Lambda square minus 1 equals 0, which implies that lambda is plus minus 1. So we have to perform the PBH test for eigenvalues 1 and 3. So for lambda equals 3, let's start with 1. Lambda equals 1. We have rank of a minus I, so this is simply 3, 0, 0, 5, minus 1, 1, 4, minus 1, minus 1, and then the C. This is a row vector, so 1, minus 1, 5. So we have 4 rows and 3 columns. So the rank is going to be either equal to 3 or less than 3. So let's see if the 3 columns are linearly independent or not. So we have C1, C2, C3. Let's see. We have alpha 1, 3, 5, 4, 1. Alpha 2. So you can simply see the first equation that implies that alpha 1 is 0. Last equation was that simpler. Alpha 1 minus alpha 2 plus alpha 3 equals 0, which implies alpha 3 equals alpha 2. Alright, so we have two conditions as of now. Let's see the second equation. 5 alpha 1 minus alpha 2 minus alpha 3 equals 0. This is 0, this goes away. And alpha 2 and alpha 3 are equal, so we simply have this. So we have 3 linearly independent columns, therefore the rank is 3. We cannot conclude anything as of now because we also have to check for lambda equals 3. So let's do that. We have rank of 0 minus 3 and minus 3. Yes. Okay, and then 0, 0, minus 1, 5, 4, minus 1. Then we also have C, that's 1, minus 1, 1. Okay, so one of the things that you can observe is that this row is 0, so you can just check if these 3 rows are linearly independent. Or as you have done for lambda equals 1, you can check if these 3 columns are linearly independent. So let's check if these 3 rows are linearly independent or not. For 1, 5 minus 3 minus 1, 4 minus 1 minus 3, alpha 3 times 1 minus 1, 1 equals 0. So the first equation is 5 alpha 1 plus 4 alpha 2 plus alpha 3 equals 0. Then we have minus 3 alpha 1 minus alpha 2 minus alpha 3 equals 0. So we have 3 equations and 3 unknowns. We need to find if alpha 1, alpha 2, alpha 3 are 0 or not. check. Okay, so let's see if we can simplify this. We can substitute alpha 3 from here. So we have equations are 5 alpha 1 plus 4 alpha 2 equals 0. Simply 2 alpha 1 plus 3 alpha 2 equals 0. So we have this. And then similarly, we have minus alpha 1 minus 3 alpha 2 minus 3 alpha 1. This is simply that alpha 1 plus alpha 2 equals 0. You can either substitute alpha 1 equals minus alpha 2 here, and we get minus 2 alpha 2 plus 3 alpha 2 equals 0, which implies that alpha 2 is 0. And this alpha 1 minus alpha 2 implies that this is. And finally, this implies that alpha 3 is also 0. So we have 3 linearly independent rows, therefore the rank is 3. Therefore, we conclude that the pair CA is detectable. Alright, so now we have to find L such that A plus LC is a Hurwitz matrix. So recall that we can only find such an L if the pair CA is detectable. Oh, sorry, observable. So recall that for part B, pair CA is observable and again matrix L such that A plus LC or A minus LC has desired eigenvalues. So since we want the matrix to be Hurwitz, we can specify the eigenvalues at some, let's say, lambda d is -1, or anywhere on the left half plane. So we just want the matrix A plus LC to be Hurwitz. We can also choose this to be something else as long as it is in the left half plane. Okay. So we'll first have to check whether the pair CA is observable or not. So the observability matrix is, I'm going to write this down directly. This is 1 minus 1, 1, 2 minus 1, 1, 1, 1. So you can easily see that these two rows, these two columns are linearly independent. This is C1, C2, C3. You can easily see that C2 is minus C3. So the rank of the observability matrix is not n, which implies that the pair CA is not observable. So if we do not have a system which is observable, then the question is how do we design the gain matrix N? So since the system is not observable, we will perform the observable decomposition. So let's do that. After performing the observable decomposition, we'll have a reduced pair C0, A0, let's say, which will be observable. And then we can find the gain matrix L for that system and then extend it to the system of order 3, which is N here. Or let's say. So for performing the observable decomposition, we need a similarity transformation. This is similar to the case for performing controllable decomposition to get the standard form. So let's see. T is, so we have to find a transformation matrix T. So T should be invertible. So to get T, we select two columns which are linearly dependent from the observability matrix because the rank is, I think, 2 here. It's 2. So there are two linearly independent columns. So you can choose 1, 1, 1. You can also choose 1, 2, 5. And then maybe another column which is linearly independent. I'm choosing -1, -1, 0. You can also choose some other column. Or to simplify this further, you choose 1, 0. So there is no unique T which you can compute. So you can have various combinations. So using this transformation, I am considering the new state to be Z, which is T times X. Therefore, we have Z dot equals Tx dot which is T inverse Z plus TBU. And similarly, we have Cx, which is C T inverse Z. So this is the new A matrix. Let's say A bar. This is B bar. This is C bar. So we already have A and we have also found a transformation matrix T. We have chosen one. So I'm going to write this down as A bar equals TA T inverse. You can compute T inverse, substitute that here. I'm going to write this down directly. This is 0, 1, 0, minus 3, 4, 0, minus 2, 3, minus 1. Similarly, we have C bar, which is C T inverse, that is simply 1, 0, 0. So we have this in the standard form now. You can see. So we have to, since the rank of the observability matrix is 2, so we are going to have a second order system, subsystem from this, which is observable. So that is A0, which is 0, 1, minus 3, 4, and C0. You can just check if this is observable or not. You can check this later. I'm going to simply write this down. That the pair C0 E0 is observable. O bar, which is C0 and C0 is 0. So it's 0. So we get 0 and 1. So this is simply the identity matrix. So the rank is 2. Therefore, the pair C0 A0 is observable. Alright. So let's say that the gain matrix for we have the original system for which we have to design A plus LC to be a Herbert's matrix. So this is row vector. So 1 by 3. This is 3 by 3. So L is going to be 3 by 1. So let's say L is some L1, L2, L3. So out of this, we select a reduced matrix, let's say L bar, which is L1, L2 for the second order system C0, A0. So since the pair C0, A0 is observable, we can design this matrix such that the matrix A0 plus L bar C0 is hermits. So what is this? This is 0, 1, minus 3, 4 plus L1, L2 and 1, 0. One, one, eight. Check this out. Just 1 second. This is let me know if there is some incorrect compilation before. 0, 1, minus 3, 4. And 0, L2, 0. Okay. So the characteristic equation for this equation is characteristic equation for P0 plus L bar, let's say C0 is of L1 minus S, 4 minus S, equals 0. So this becomes, now let's expand this quickly. This is 4L1 minus SL1 plus S square minus L2 plus 3 equals 0. S square minus S, then we have 4L1 minus L2 plus L3. So plus 3 equals 0. Now we want the whole system to be Hilbert. So let's say that this reduced system A0, C0 is also Hilbert's, and let's say that the desired eigenvalues are at minus 6, minus 6. Desired eigenvalues, we are going to locate them at minus 6, minus 6. Alright, so in that case, we simply have S plus 6 square equals 0. So we get S square plus 12S plus 36 equals 0. So now we can simply compute the coefficients. Sorry, compare the coefficients. So We have minus 12 equals 4 plus L1, 16. And then we have 4L1 minus L2 plus 3 equals 36. L2 is 4L1 plus 3 minus 36. So we have 64 plus 3 minus 36. This is minus 97. Okay, so L bar is minus 16 minus 97. You should note that we have computed the gain matrix for the second order system A0, C0, and what we need is L equals L1, L2, L3 for the original third order system. So let's say that these came from here. So this is minus 16 minus 97. And now we have to assume some value of L3. So let's assume that this is 0. Since we are talking about the transformed system, we have transformed the system to the standard form for an observable system. So for the original system, the gain matrix is T inverse L. So I'm going to write this down directly. You can compute T inverse and multiply this by L. This is minus 81, 65. So now you should observe that although we have computed the gain matrix for the original system, our job is not done. We still have to verify whether the eigenvalues of A plus LC lie in the left half plane or whether A plus LC is Hurwitz or not. This is always very important to verify at the end. So A plus LC is 0, 0, 5, 0 minus 1, and then L is minus 81 minus 65, so 1 minus 1, 9. So that plus L in matrix for the original system. Let's compute A plus LC quickly. This is plus we have 3, 0, 5, 0 minus 1. Okay. So we have this here. Okay, so now we have minus 65 minus 1. Then we have minus 60. Then we have minus 78. Okay. And now we can just check that whether the matrix A plus LC is values or not. So if the eigenvalues of A plus LC lie in the left half plane, then you're done. If not, then you'll have to choose a different value for this last entry L3 and then repeat the procedure from here. So I hope that this question was clear to you. So what we have done is, since the pair CA was not observable, we have transformed the system to the standard form for an observable system. Then computed the gain matrix for the observable subsystem C0, A0, and then extended it to the third order system, which is the column gain matrix L1, L2, L3, and then formed A plus LC. If the original system was observable, we don't have to perform the observable decomposition. What we can do instead is select three desired eigenvalues, let's say repeated at -6. So lambda t is -6, -6, -6. We can compute the desired characteristic equation and then compare its coefficients with A plus LC. That is a characteristic equation for A plus LC. But this question was clear to you. Now let's move on to the next one. Consider the system. X dot equals 1, 0, 0. Times x. We don't need the b vectors. This we're talking about detectability. And then we have C1, C2, C3 times x. C1, C2, C3 are unknown scalars. So we have done similar questions for controllability and observability. Provide the necessary just 1 second. Provide a necessary and sufficient condition. Conditions on Ci, on C1, C2, and C3 such that the system is detected. So for this, we need to recall the necessary and sufficient conditions for detectability. So we must recall the eigenvector test for detectability. LTI system detectable and only if every eigenvector of A such that real part of lambda is greater than 0 is not in the kernel of C. So kernel of C is the subspace, let's say V in R3 for our case, yes, such that C applied to V is 0. So we want those vectors such that CV is non-zero. Alright. So first we need to determine the eigenvalues of the matrix A and then compute the eigenvectors for all lambda such that their real part is greater than or equal to 0. So let's see. I equals 0. So we have minus lambda, minus lambda, minus 1 minus lambda. Zeros everywhere else. This is 0. So this is good since we have a diagonal matrix. The determinant is simply 1 minus lambda, minus lambda, minus 1 minus lambda equals 0. This implies that eigenvalue is minus 1. This is 0. So this is plus 1. This is minus 1. So for the eigenvector test, we are going to consider only these two eigenvalues. Alright, let's see. For lambda equals 0. This is going to be AV equals lambda I, which is simply the 0 vector. Sorry, lambda V. Alright, so A is 1 0 0 0 0 0 0 0 plus 1. And then we have some eigenvector v1, v2, v3. So first equation implies that v1 is 0 and the third equation implies that v3 is 0. And since we don't have an equation on v2, we can simply say that v2 can be any real number. So the eigenvector corresponding to 0 is, let's say 0, some a, 0, where a belongs to R. Then we have for lambda equals 1, we have to solve the equation a minus I applied to v equals 0. Because we're talking about a v equals v. Okay, so a minus I is simply 0 here, minus 1, minus 2, and 0 is everywhere else. Okay, so we have the second equation which implies v2 is 0, and third equation implies v3 is 0, and we have no restriction on v1. So we have, say, a 0 0, a can be any data, or let's say this is b. So let's choose some values of a and b. Let's say that we have a equals 1, b equals 1. So the two eigenvectors are 0 1 0. On that c applied to, let's name this v1, this as v2, should be non-zero, and C applied to V2 should be non-zero. Alright, so let's see. We have C1, C2, C3, and 0 and 0 implies that C2 should be non-zero. Similarly, we have C1, C2, C3. This should be non-zero, which implies that C1 should be non-zero. So observe that we have no condition on C3 such that C times V is non-zero. So there is no condition. C1 has to be non-zero, C2 has to be non-zero, and C3 can be any. These are the necessary and sufficient conditions. Condition for the pair CA to be detectable. Right, so I'm going to wait for a few minutes. If you have any doubts, you can ask me now. So if there are no doubts, let's move on to the next question. Consider the following ATI system. X dot equals U1 minus 1 and Y equals 1 times X. So the objective is to design a full dimensional reduced dimensional state estimator system given below. And select the eigenvalues. So the eigenvalues are eigenvalues of the estimator. From the set -3, -2, plus minus 2j. So so we have been given a choice to select the eigenvalues from a given set. Or have a second order system, and if we have to select eigenvalues for a second order system from this set, then they should be -2 plus minus 2j. Because if eigenvalues of a system are complex, then they should occur in complex conjugate pairs. Alright. So the desired eigenvalue. So let's say the first part is design of full dimension estimator. So this is design of. So the desired eigenvalues are -2 plus minus 2j. So the desired characteristic equation is S, let's say S plus 2 plus 2j, then S plus 2 minus 2j. This is simply S square plus 2S. Then we have 2S plus then we have 2js plus 4j minus 4j squared. So yeah, let's see, this goes away and this also. Okay, so we have S squared plus 4s and plus 8 equals 0. Alright, so to place the eigenvalues at these locations, we first have to check whether the pair is observable or not. This is going to be easy. We have a second order system. This is C8. So CA is 2, 1, minus 1, 1. 1, 1. Alright. So we have and therefore we get 1, 1, 1, 2. So the determinant is non-zero. Therefore the pair CA is observable. Alright, so this means that we can place the eigenvalues of A minus LC or A plus LC at the desired locations. Alright, so let's say that we are considering A minus LC. This is going to be 2, 1, minus 1, 1. This is plus L1, L2, 1, 1. This becomes L1 and L2. So this is 2 plus L1, 1 plus L1, and similarly the next one. Again, let's quickly compute the characteristic equation. This is 2 plus L1 minus S, 1 plus L2 minus S, and the off-diagonal entries remain as it is. Let's compute this. Minus S All right. So it's going to be a long expression. I'm going to write this down directly. You can expand this and check. So I have s square minus s. So s is going to have 1 plus L2 and L1. This is 2 minus L1 plus 1 minus L2. Then we have 2 plus L1 times 1 plus L2 minus 1 plus L1. That 2 minus 1 equals 0. So this is first equation. This is the second one. So I'm comparing the coefficients. So you can compare each of them. So 2 minus L1, the component of S is 4. So I'm going to write the values of L1 and L2 directly. So this becomes 4 minus 3. So we can check this later. And then one way to verify is you can just simply compute the eigenvalues of A. Thus, let's see. So verify by computing the eigenvalues of A plus LC. They should be located at minus 2 plus minus 2J. Now we'll talk about the reduced dimensional state estimator. I have the matrices A and B. I'm going to write this down again. A was 2, 1, 1, 1, and C was 1, 1. So we have n equals 2. So I'm going to refer to slide 18 of the lecture. Okay, so we have n equals 2 and output is 1. So we have q equals 1. So C has rank 1 because it has only one row. Step 1 is to select an arbitrary stable matrix F of size n minus 2. So we just have to select one by one scalar which is stable. So stable matrix means we need an eigenvalue in the left half plane, and so this is just a scalar. We can select this to be any value. So let's say f equals minus 3. There is further instruction on f that the eigenvalues of f should not be common to those of A. So let's first verify the check the eigenvalues of A. I think I've done this before. Yeah, okay. So again, we have determinant of A minus lambda I. Which implies have 2 minus lambda, 1 minus lambda. Get And 2 minus 2 lambda minus lambda plus lambda square plus 1 equals 0. Okay, so here's the eigenvalues. You can just see these. Plus 3. So these are complex and they will never be equal to minus 3. So we can select f as minus 3. Alright. Now we have to select an arbitrary matrix L of size. So this should be of size n minus q by q. So we have again 1 by 1 such that FL is controllable. The pair FL is controllable. Alright, so we already have f is minus 3. We can just select L to be, let's say, 1. And this, of course, is also controllable. Alright. Now we have step 3. We have to find the unique matrix T of size n minus q. So this is 1 by n. So that satisfies the Laplace equation. So such that it satisfies Ta minus Ft equals Lc. So T is going to be, let's say, T1, T2. We can substitute this in this equation. We already have A, F, N, and C. We will have two equations and two unknowns. We can find out what T1 and T2 are. So I'm going to write this down directly. Matrix T comes out to be 1, 0. Okay. Next step is step 4. So we have to find the matrix P, which is C and T, arranged row wise. So C is, let me just check. C was 1, 1, P is 1, 0. Determinant of P is minus 1. That P is non-singular. Okay, so if P was singular, we will have to go to step 2, select L such that again FL is controllable, and then repeat step 3 and step 4 until we get a matrix P which is non-singular. Alright, so we have the matrix P, and step 5 is the state equation. So we have n minus q equals 1 dimensional state equation. That is z dot equals fz plus tbu plus ly. So we have f, t, b, and l. We can substitute this to get the state equation for the one-dimensional reduced system. And the estimate x hat is going to be ct inverse, which is p. So that's why we needed p to be non-singular so that we can take its inverse times yz. So this will generate an estimate of the original system, original nth order system. Estimate of x, which for our case is in R2. So let's see what is P inverse. So x hat is P inverse times yz. So determinant is -1. Swap the diagonal elements and reverse the sign of the off diagonal elements for a second. This is for a 2 by 2 matrix times y z. So 0, 1, 1 minus 1. So we have the output y. Then we can solve the state equation for z and find what z is. And then the estimate for the whole state x is simply z and y minus z. So this is the state of the reduced estimator. And this is again the output, which you already have. So output is a scalar and we have two states. So the two states are estimated as z and y minus z. Alright, so I hope that this question is clear to you. Now let's move on to the last question of the day. This is simply determine the observable canonical form. Following LTI system. So we have x dot equals to 1 minus 1 1 x plus 1 u and y equals 1 1. Okay. So we also discussed it in the last week's tutorial session. What we can first do is convert the system to the controllable canonical form. And then by the principle of duality, we can get the observable canonical form. Or so we know how to get the controllable canonical form, and just recall that if we have a transfer function gs, let's say v1 is to the power n minus 1, and so we need the transfer function to be strictly proper. So therefore, the order of the polynomial in the numerator is s minus n to the n minus 1. Then we have s to the power n, that's alpha 1, so on till alpha n. And if we have this general transfer function, and the A matrix in the controllable canonical form is simply, so it has to be a chain of integrators 0, 1, 0, 1 keep shifting on the right. Number 1. And then the last entry is alpha 1, alpha 2 till alpha n. For B, it's quite simple to remember. We just need the input to be in the last term. So zeros and 1. And C becomes, so we can calculate C from the numerator polynomial. This is simply beta 1, beta 2, till beta. And if you have these in the controllable canonical form, then in the observable canonical form is simply the transpose. BOCF is BCCF transpose. So this is the relation. So we already have seen the OCF. This is simply zeros and then 1. Okay, so for our case, we need the transfer function first. So GS is simply C SI minus A inverse times B. We have D equals 0. Alright, so SI minus A is going to be S minus 2, S minus 1, minus 1 plus 1. Let me just check if this is correct. S00S minus 2, 1 minus 1, 1. Yes, alright. The determinant is so we have S squared minus S minus 2S. Alright. So S and minus A inverses 1 upon determinant times S minus 1, S minus 2, 1 minus 1. Alright. So G S is C times. So C is, let's take this out first, times C and then we have B as 1. Alright, so you can calculate this. I'm going to write this down directly. This is 3S minus 6 or S squared minus 3S plus 3. Now you can simply write alphas and betas, right? So beta 1 is 3, beta 2 is minus 6, alpha 1 is minus 3, alpha 2 is 3. So ACCF is going to be 0, 1, minus 3, 3, and CCCF is going to be beta 1, beta 2. We already have BCCF over 0, 1. Now we can just compute our CF, which is this becomes minus 3, 3, 3 minus 6, and finally we have CCF transpose, which is 0, 1. So for any given LTI system, you can compute the transfer function, and then you can compute the controllable canonical form, and finally get the observable canonical. So I hope that this question was clear to you. Alright, so that's it for today. We have covered the topics from the last week's lecture. If you have any doubts, you can ask me. I think there is a link already. Let me share. You can open the course page and yeah, there is, I think, the last tab, problem solving session, January 2025. And then there, I think there are recording and notes. You can check it now and let me know if you can open your readings. Yeah, I'm sure actually about that. I think there was an announcement, right? Yeah. Yeah, I think the professor has not mentioned whether it's going to be an objective type or a subjective type question. So, uh, maybe what you can do is you can post this question on the Q&A forum. Do you know where it is? Yeah, just ask that there. I think the professor would answer that because I'm not sure about the format of the. Yeah, I also would like. That's why you need to ask on the forum. All right, if there are no more questions, then I think we can leave for today. All right, then. That's good then.